Okay, something similar to this question is a problem that I find it very interesting since I was a kid. So let's call it exercise 3. So it is about, let's take a look of this thing, okay. So 1 divided by 1, okay, it is 1, am I correct? 1 divided by 2, it is equal to 0.5, okay. 1 divided by 3, it is equal to 0.3333. And then because 3 will repeat, so there is a way to represent this. So I have a dot here to represent this part is going to repeat forever. So this is 1 over 3. Is that okay? And then 1 over 4 is equal to 0.25. Nothing to stop, right? 1 over 5 is equal to 0.2. 1 over 6, it is equal to 0.16. So the 6 dot here means that the one you do not repeat, but it is 166. Okay? And then this is a magic number 1 over 7. 1 over 7 is like 0.142857. And then the repeating thing is from 1, 4. So 1 over 7 is equal to 0.142857, 142857, 142857. So this is, you are going to repeat 6 digits forever. And then 1 over 8, 0.125. Let's write down 2 more. 1 over 9. 1 over 9 is 0.1. You have a dot here. And then 1 over 10, it is like 0.1. Okay? Now, so far, what we have seen is that there is a certain kind of pattern. The pattern is that either when you divide an integer by 1, so divide 1 by an integer, either you will get something that stops. It is not recurring. It just stops. 0.5, it stops. Or if it goes on forever, then it will be becoming a recurring fraction, so a recurring real number, so 0.333. Is it always true? So will it be something that is very strange, that you will not find it recurring? So there is some number that you will not be recurring, like pi, the pi, 3.14, blah, 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 blah. It is not recurring. Like e, it's not recurring. Like what? Like square root 2, it is not recurring. Okay? But here, we want to show that all the fractions, so if 1 is divided by an integer, then it is always going to lead to either a fraction that you stop. Okay, so it is a real number that you stop. Okay, or it is going to recurring forever with a recurring pattern. Okay, so I'll leave this as an exercise. Think about this, perhaps make it as an assignment. This is something that so here, actually, we want to show that no matter what number you are looking at, even if the number is like 2017, 1 over 2017, it will still be recurring. Okay, maybe the recurring part is very long, but it is either recurring or it stops. Okay, and okay, of course, if you think more about it, you can also find out what is the rule. So how do you determine if a number, after divide this number by 1, it will stop? So 4 will stop, 2 will stop, 8 will stop, 5 will stop, 10 will stop, right? So what numbers will stop and what numbers will not stop? Okay, so this is okay, so let's make this as a challenging question in your homework, maybe. So I will continue with another example, okay? But this is related to, I think, related to this thing, okay? To the second problem. Okay, for the next problem. So let's call it exercise 4 or example 4. Now, let's consider n squared plus 1 distinct integers, distinct numbers. So for instance, let's say n is equal to 3. So in that case, we are looking at 10 numbers, okay? Distinct numbers forever. So for instance, I can write down as 2, 3, 1, 4, 6, 8, 7, 5, 9, and let's make a 0 there. Okay, so there are 10 numbers here. Then we want to show that no matter how you write down these n squared plus 1 numbers, you will find a length n plus 1 increasing subsequence, or you will find a length n plus 1 decreasing subsequence. Okay, so what is subsequence? Subsequence is that you take the numbers. Maybe I take this one, this one, this one. So you take them out and arrange them according to the original order in the sequence, then it is called a subsequence. So 2, 3, 4 is a subsequence. 3, 1, 4 is a subsequence. 3, 4, 6 is a subsequence. 3, 6, 7 is a subsequence of this one. But 7, 6, 5 is not a subsequence, because 7, 6, 5, you go back and you go forward. This is not good. Okay, it must go from left to right. Okay, so here in this example, so in this theorem, it is guaranteed that you will always find either this one or both, a subsequence of long enough length. So okay, so we're lucky. Okay, so if you look at 2, 3, 4, 8, then this is a subsequence of length 4. Okay, okay. Now notice that again, this is like the solid triangle and dotted triangle case. We are not saying that we will always find both. So obviously, this is not always true to get both, because maybe you are already arranging the sequence as increasing. So it is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then in that case, you can't find a decreasing one. Okay? Is that okay? Now again, for this one, for this problem, if we change it, so what does it, so here, so this example says, if we have n squared plus 1 distinct numbers, then it guarantees that we will either find this one or both. Okay? Now this is also a very tight result, because if we just have n squared distinct numbers, then we don't have any guarantee. We don't have any guarantee to get n plus 1 increasing or n plus 1 decreasing. How? Or, so I'll just give you a very simple counterexample. So when n is equal to 3, then we get what? So let's look at numbers from 1 to 9, okay? Because n squared is 9. Okay, 1 to 9. So let's get 7, 8, 9, 4, 5, 6, 1, 2, 3. Is that okay? So I'm actually arranging the numbers into blocks of n numbers. N numbers here, n numbers here, n numbers here. The largest n here increasing, and then the next largest n increasing, and then the next largest n increasing. Is that okay? Okay, then you see that the longest increasing must be of length 3. You cannot get length 4. If you get length 4, you will need 2 blocks or more. And then if you have 2 blocks, let's say I'm getting a number from this block and a number from this block, you can't be increasing. Does that make sense? Is that okay? And similarly, if you want decreasing, you cannot get numbers from the same block. If I get 2 numbers from the same block, let's say 7 and 9, then the subsequence cannot be decreasing. Does that make sense? So here, each block has n numbers and there are only n blocks. So the longest increasing is of length n, and the longest decreasing is also of length n. So you don't see n plus 1 subsequence of increasing or decreasing. Okay? Very strict. So n square number, no guarantee. N square plus 1 number, suddenly, no matter how you do that, it guarantees. So this is another amazing result. I think, yeah. It's just like the 6 people problem. 6 people, no guarantee. 6 people guarantees. 5 people, no guarantee. So it's very, very tight. Okay. Okay, how do we prove? Okay. This is difficult. How do we prove? So suppose that let's write down an example with n squared plus 1 numbers. So let's say to illustrate our proving technique. So let's write down the numbers again. So let's say 4, 2, 7, 8, 5, 3, 6, 1, 9, 0. Is that okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So let's have this. Now, to prove this, we define a new concept called, so we are going to define a concept or a parameter associated to each position. Okay. So for this position 8, okay, we want to ask, what is the longest increasing, what is the length of the longest increasing subsequence starting with this number? Okay, so longest increasing here is 2. Very good, 8, 9. So we get a 2 here. So longest increasing for this number is 2. And then what is the longest decreasing starting from this number? Longest decreasing, it must include this number. So what is the longest decreasing? Length. So maybe equal to 5, right? So you get 8, 5, 3, 1, 0. Is that okay? So it is equal to 5. Okay? So this position, you have these two magic number, 2, 5. Longest increasing is 2, longest decreasing is 5. Okay? How about this one? Let's say this position. So what is the longest increasing? Longest increasing, it is going to be 4, 5, 4, 1, 2, 3, 4. Is it like 4? So the length is 4. And longest decreasing, 3. Is that okay? Okay. Okay. Now question. Okay, the question here is that, so each number has associated with 2 parameters. Can the 2 parameters of this one equal to the 2 parameters of this one? So if there are 2 different positions, can their parameters, corresponding parameters, be both the same? So for instance, I mean the same means that, so for instance, it is 2, 5. If it is 2, 5, then it is the same. But if it is 5, 2, then this is something different. Is that okay? So if I have 2 different positions, let's say this position and this position, so in general, can any 2 positions have the same pairs of parameters? No. No. Reason. What is the reason? Okay. So that's true. 2 different positions must have distinct pairs as their parameter. Reason is that if this one is smaller than this one, like this 2 and 8, then the increasing part, this one must be larger than this one. Does that make sense? You cannot have the same. On the other hand, okay, reverse. Let's say if this one is larger than this one, then the decreasing part, this one must be longer. Does that make sense? Yeah, because we always include this one, so you can include one more, so it must be longer. Okay, so we establish this. Every position so must have distinct pairs. So the pairs must be distinct, okay? Is that okay? Okay. Now we claim that for n squared plus 1 numbers, we must either see an n plus 1 increasing or n plus 1 decreasing. We want to show this is true by contradiction. Okay, by contradiction. Okay? Think about the arguments that we want to form. So we want to show that by contradiction that this is true. So what do we assume? Assume that you do not see n plus 1 increasing, n plus 1 decreasing, right? So what does that mean? So that means that the longest increasing is only n. The longest decreasing is only n. Is that okay? The longest increasing is only n. The longest decreasing is only n. How about the shortest increasing? What is the shortest increasing? 1. And the shortest decreasing? 1. Is that okay? Now, if we know this is true, longest increasing is only n, longest decreasing is n, shortest increasing n at 1, shortest decreasing 1, then what is the effect on this parameter? Then, in this parameter, we don't see n plus 1. All the numbers here must be chosen between 1 to n. Am I correct? All the numbers must be between 1 to n. Okay? So how many different options we can have? So you can have 1, 1, 1, 2, 1, 3 up to 1n, 2, 1, 2, 2, 2, 3 up to 2n. So there are only n square options that we can have. Right? But then you get a contradiction. There are n squared plus 1 positions. We have only n square options. Pigeonhole principle says that 2 of the positions must have the same choice. And then it contradicts to the fact that every position must have distinct pairs. Is that okay? So the Pigeonhole principle is only used in a very, very minor place. But still it is using. We are still using that. Can you see this? Okay. So recap, okay. So we define the concept of pairs associated with the positions. And then to prove the theorem, we are using contradiction. So if the contradiction part is true, then that means that all the numbers we see here must be between 1 to n. Then in that case, there are only n square options. But Pigeonhole says, if you have m squared plus 1 position, you need to choose n squared plus 1 pairs, but then you have only n square choice, then 2 of the position will need to use the same pair. And then this contradicts to the fact that every position must have distinct pair. Okay, when you have a contradiction, then that means that your assumption at the beginning must be wrong. So it's wrong to assume that you don't have any n plus 1 increasing, n plus 1 decreasing. So that's true. Okay, let's take a break. Let's take a time. So let's come back at 3:20, and then we will continue with some more examples.